The next topic we'll get into now is the idea of what momentum is. And it turns out momentum, like energy, is conserved. So this little video here is an introduction to momentum and the conservation of it thereof. So the first thing about momentum then is let's just get a couple definitions out. Given the symbol P, and is equal to an object's mass times its velocity. So the symbol P, I realize it doesn't start with an M for momentum, but there it is there. And it might look like a familiar equation. You might be thinking, well, haven't we done this before? Because we've already done ma. Well, no, that was F. That's not mv. Thinking, well, we've already done 1/2 mv squared. We're saying, well, no, that's kinetic energy. It has an m and a v in it, but no 1/2 and no squared. So that's kinetic energy. It's not that either. So indeed, momentum is a unique quantity. It comes from multiplying an object's mass times its velocity in this case here, and that's the definition of it. So one more thing about momentum is because this v here can potentially be a vector when it's called velocity here, then we might say then that the momentum itself must be a full vector like that. So indeed, P is equal to m times v vector. So it's a vector equation. But of course, what that means, whenever you have a vector equation, then it means that x momentum is equal to m times x velocity, and y momentum is equal to m times y velocity. So the vector equations can always sort of be expanded into their component forms, and those are the ones that we can use. So that's the definition of velocity here. Or excuse me, definition of momentum here is object's mass times its velocity. And so you might sort of link that a bit to some colloquialisms right here. What does momentum really mean? Well, we hear momentum from time to time, like say the momentum, say, of a big truck. So you have like a big truck hauling down the road and you go, man, it must be hard to stop that truck because of all the momentum it has. Indeed, that would probably be true. Big truck has a lot of mass. It's made out of a lot of metal. It's even traveling at some relatively small speed. The product of the two might still be a really large number, so it might have a lot of momentum, as you're saying here. What about the momentum, say, other times you hear it, of the stock market? Say, well, the stock market's really doing bad. It has a lot of momentum. It would be hard to recover from. Or the stock market's on the way up. It has a lot of positive momentum lifting the market up. You might think of it that way. It doesn't have anything to do with MV in that case for a stock market, but just sort of implies the property of motion of some object that you might expect is going to persist or be hard to stop, the momentum of something, like of a big truck or a big football player or of the stock market, whatever the case may be. So that's sort of where we hear about the word momentum in things, and that's the physics definition. And so then the last part of the video here is about this idea of conservation of momentum. So the ideas for conservation of momentum should be very familiar to you after having just studied conservation of energy. But what it sort of tells you then is that as a vector, the initial momentum of a system is always going to be equal to the final momentum of a system here. So you can sort of an equality like that, which looks very much like conservation of energy, where you said that the initial energy of the system is equal to the final energy of the system. So it's sort of like this. The differences, of course, are that energy is not a vector, momentum is, and also there's different types of energy, like there's potential and kinetic energy, and even under potential there's different types of energy. There's spring, and there's pendulum, and there's gravitational potential energy. Well, there's only one kind of momentum, just m times v, and that's all you get. It's a vector here. So a couple things here is that, of course, being a vector equation, once again, we can write this instead of p initial x is equal to p final x, and p initial y is equal to p final y. So those would be, of course, the usable forms of the equation that would sort of break the vector down and look only at the components. But of course, you can have multiple momentums in a problem. So what does momentum mean again? It means that something is just, you multiply something's mass times its speed, or mass times velocity, as in the case here. But you can have more than one object moving. You could have two cars heading into each other, or a whole bunch of cars going in different directions. Each one would have a momentum insofar as the problem is concerned. And so really these equations here should instead be expanded to say the sum of the initial x momentum is equal to the sum of the final x momentum. And the sum of the initial y momenta is equal to the sum of the final y momenta, something like that. So these will be our guiding equations for solving problems that have to do with this concept of conservation of momentum. These will definitely be our guiding equations here. We'll look no further than these. And why is it conservation again? Because we're going to add up a bunch of momentums that happened initially in the problem, assuming none got lost anywhere, and we're going to set them equal to the final momentums of the problem, even sum them all together again, assuming nothing got lost. And that's exactly the idea of conservation. So you can have some momentum here to start a problem, either here or here, and then something can happen, and in most cases it'll be a collision or some action will happen, and we'd expect to recover all of that momentum back out. Maybe in a different form, maybe got transferred from one object to the other, or one object has less or more momentum than it had before, But the idea that we can set them equal is exactly the implication of conservation, that nothing got lost between the two states of the system, say before and after, and that's where conservation will come from. So we'll start a lot of conservation momentum problems by just writing these two equations at the top of the page and just going forward with them.